All right, everybody. Thanks for coming out. Appreciate the standing room. This is pretty awesome. Really glad to be here at Big Data London to talk about DuckDB at scale and how DuckDB scales and how we at MotherDuck have probably the largest DuckDB fleet in the world. Although given the rate at which DuckDB is growing, chances are that's going to change. That may change in the future. So how many people are DuckDB users? Actively DuckDB users. Okay, so I guess there's how many people are DuckDB curious? How many people are just here to throw stuff at me? I see some ClickOut shirts in the back. I bet no, just kidding. But first, let me introduce the flock. So who am I? I'm Jordan Tigani. I've been a database person for about the past 15 years. I worked on BigQuery for 10 years. I was trying to calculate. I think we ended up querying a zettabyte by the time I left. Worked at SingleStore for a couple of years, and about 3 years ago, I encountered DuckDB and saw like, wow, this is an amazing piece of technology. Somebody should really take this and build a cloud service out of it. At first, I talked to Hannes and Mark, the DuckDB founders, to see if they were interested in hiring me to maybe help them build a cloud service, and they said, well, we really would just want to focus on the technology, and so but we'd be happy to partner with you. And so kind of after that moment, the DuckDB partnership and MotherDuck partnership was formed. So what is DuckDB? In case people don't know, it's an embedded SQL database tuned for analytics, and it has some really nice properties. It scales down really nicely. It's embedded, so you can actually link it into anything you're actually building. It has really nice connectors to most languages. Here's an example in just 4 lines of Python. You can write your first DuckDB query. DuckDB has also been really accelerating in popularity. I think it has 30-some thousand GitHub stars at this point. The number of downloads, they just shared with me that they're doing a petabyte of extension downloads a month. So that's a lot of people running. DuckDB. So why do people like it so much? I like to think of it as the burgers. Most databases they focus just on the patty of the burger. Certainly, when I was at BigQuery, we did this. Like we said, okay, well, once you give us your data, you send us your query, then we'll try to optimize that query, run it really fast, and then give you the results as fast as we can. But like anything outside of that is your own problem. And DuckDB, for example, they have like full-time engineer, PhD, working on their CSV parser, and they've been working on it for years, and they're still working on it because they want to make it better and better and better. In BigQuery, we had a new grad working on our CSV parser. They spent a couple months on it, and it was like, okay, cool, that's done. Now we're on to the next thing. But if you think about like what actually takes you time as a data analyst, data engineer, data person, it's like, how do I get this damn data that's over here into this other place that's over here? And DuckDB makes this really nice. In fact, for my demo, I was going to show comparisons to BigQuery, and I just got frustrated with how hard it was to load data from S3. And so I gave up. And that's the kind of thing that DuckDB they focus on doing really, really well. So what's MotherDuck? So we're taking DuckDB and we're hosting it in the cloud. So we're building a SaaS version of DuckDB. We run lots of DuckDBs. One way of thinking about it is it's just a data warehouse. It's a really low latency, easy, inexpensive, great data warehouse. On the other hand, it's being able to take the DuckDB you know and love and just have somebody else run it for you. These are the same 4 lines of code that I had for DuckDB. The only thing you need to do to start using MotherDuck is change the file name to start with MD colon. And if you start with your file name with MD colon, it loads the MotherDuck extension and it'll actually run in the cloud. So MotherDuck is serverless, spins up instances on your query. So within 100 milliseconds, we'll assign you a DuckDB instance, which we call DuckLake. We use warm storage, so it actually can be very fast for cold start, which allows us to sort of spin up instances and spin down instances. But we also have some very large instances, and kind of the tenancy model allows you to run one DuckDB instance per end user. Because one of the tricky parts about DuckDB is, it's really focused for a single workload at a time. And so we say, fine, use a single workload at a time. If you have lots of workloads, each one is going to get a different DuckDB instance, and each one can scale independently. The other exciting thing is that next month, DuckDB is launching our first European region in Frankfurt at AWS. Because DuckDB was created in Amsterdam, there's a lot of excitement for around DuckDB. So we're really happy to partner with a bunch of folks in Europe to help spread the duckiness as much as possible. So what have we learned from running giant DuckDB instances? Well, first, I want to address the elephant in the room. We're at Big Data London. I suppose everybody knows that. I also wrote a blog post a couple of years ago called "Big Data is Dead," where I talked about, hey, big data is no longer a relevant term. So what am I doing at Big Data London? Well, so given that we're in London, I figured I would start with a Shakespeare quote from Julius Caesar, suitably duckified. I come not to praise big data, but to bury it. And I'm not quite that anti big data. It turns out sometimes in order to get a catchy title, you need something very black and white. But of course, there's lots of shades of gray. So we looked at the data about what data people are using. So there's a couple of data sets that have been provided by some of the other data warehouse providers about how their technology is going to be used. So one of them is called Snowset, Snowflake's data set, and then another one is called Redset, which is Redshift's data set. And they wrote a paper on, they basically were making a claim that the shape of the data analytics benchmarks are not quite right for for modern workloads. But it also provided a really nice window into the actual sizes and shapes of data that people are actually using in the real world. It turns out that most databases are smaller than 10 terabytes, so we're going to call those not really big data. Of the time when you do have a big data database, you end up only querying a small portion of it. So, only 1% of the time when you have big data do you actually query, query the tables that are the big data tables, and then, of that, only 0.5% of the time, when you have big data and you're actually reading big data tables, you also read large amounts, because often when people are reading these giant tables, these giant databases, you read smaller slices. Of course, there are a bunch of patterns that do lead people to big data, and this is some of the things that we've seen. So one of the key insights, I think, is that when you think about big data, it's actually two different things. There's big data. The size of the data, the size of the data can't be stored on a single machine. You have giant amounts of data. But if you have separation of storage and compute these days, everybody just stores their data on S3 or GCS or whatever your object store du jour is. And then it turns out to be not a particularly interesting problem. I mean, storing a lot of data is, you just throw it in an S3 bucket, and it's actually kind of virtually unlimited how much data that you can store. And it's inexpensive. what's actually the real interesting part of it is big compute, is the size of compute that you need in order to access that data. Do you need actually distributed computation in order to solve your problem? And the one thing that we sort of like take for granted is just the size of machines these days. And I'll show some examples, later on. But like when we started BigQuery, getting 64 gigs of RAM was virtually impossible. Like it was basically we had to slice things very, very, very narrowly. Getting more than a couple cores was very, very difficult in a particular process. Now there's machines with hundreds of cores, gigabytes, terabytes of RAM, and tens, if not hundreds, of gigabits of network throughput. So it really changes the equation of what big data means. So I like to sort of like draw things in a 2x2 chart with the bottom left is small data, small compute. The top left is small data, big compute. The bottom right, small compute, big data. And then finally is big data, big compute. And I think it can be useful to segregate those by use cases. And if you think about where, how much these things cost, well, obviously, small data, small compute doesn't cost very much. Small data, big compute is what actually drives the costs. So if you have to do a lot of computation, it's going to be more expensive. If you have big data and small compute, often actually it doesn't cost that much because data storage prices are tend to be so low. And then really where you're going to spend a ton of money is in this sort of this top right corner, which also leads people to avoid running queries in this part of the landscape. It's what leads them to do things like the medallion architecture, where you take your data, you land it in this giant size, and then you kind of create smaller and smaller slices of it in order to reduce your query costs. Another kind of interesting thing is that for these different quadrants, there's different things that you optimize for, because in like the small data case, you really want latency. You generally very often have a user involved, and users care how long things take. If it's the difference between like 2 seconds and 200 milliseconds, like that's a huge deal in terms of if you're showing to your end users some sort of analytic or some sort of graph. Whereas at the large data sizes, what you really care about is like, okay, can we get stuff done? Can we just sort of push this through as fast as possible? I remember actually one time my manager in BigQuery, he said, if you add a second, there's somebody who was working on a feature, said if you add a second to every query, I don't care. Like adding a second to every query was considered like not a big deal, not a problem. Whereas I think because BigQuery was so far in this top right corner. So the different design goals for throughput versus latency really drive the kind of architecture you need to build. And so if you think about where 99% of all the usage is, if the design goal is latency, we tend to be using systems that are designed for throughput. So here's where some of the workloads map. I'm going to go into a bunch of these in a bunch more detail, but you can kind of see like how there are sort of real things in each part of these workloads, or each part of these quadrants. So digging into the big data versus big compute, the first quadrant is small data, small compute. DuckDB, I think probably everybody here admits or agrees that DuckDB can work great on this. It's sort of like you're doing ad hoc analytics, you're doing something on your laptop, you're doing some data science exploration. You have the sort of the platinum or gold tier if you're using the medallion architecture, or you're authoring some SQL. You want to, what's important is sort of the pace of iteration. And if you want fast iteration, then then it's nice to just have small data and small use cases. So here's a representation of some benchmark results from the ClickBench benchmark, and it was created by the ClickHouse folks, and it's too small to read because it's not. What's important isn't actually the vendors on here, but if you look at the top right corner, so like the less expensive ones are on the left, and then less expensive ones are on the bottom. Less expensive ones are on the top, faster is on the right. And so you want to be in the top right corner. So we have a bunch of small distributed databases that are pretty inexpensive. Of course, they're really slow. So you see, like these are not very fast. They're often an order of magnitude less performant. And then you have the large-scale distributed databases, which do get a lot faster, and those certainly move towards the right. But of course, those are very expensive. And then here's the DuckDB versions of these, which basically, top right corner, they're not expensive, and they're super fast, super low latency. So there's a typical problem when you have a shared data warehouse, which is sort of how typically we see people building data warehouse. You might have a single instance for your team or for your department. Is that you have sort of a lot of users hammering that same warehouse, and you end up having to provision for peak. One of the things about analytics is that the size that you need can change rapidly by orders of magnitude. And so even if you're doing auto scaling, it's sort of very hard to keep it up. So the way MotherDuck works is that every user gets their own DuckDB instance. So if you have hundreds of users, each of your hundreds of users gets a DuckDB instance, and then we can scale all those independently, because some of those are going to need a lot of data, some of them are going to need a lot of computational power, and some of them are going to be pretty tiny. Some of them are going to be very ephemeral, and we shut them down when they're not being used. So that was small data, small compute. Now, what about small data, big compute? I was originally thinking that this sort of didn't exist, and then I was thinking, well, actually, we do see a lot of these cases where, like, people are actually hitting harder than you could really do in a single DuckDB instance or in a single instance. You have, let's say, you're doing cloud-based BI, so you might have Tableau or Omni or Looker. There might be a lot of users hitting at the same time, and if those are all hitting your data warehouse, maybe they're only looking at the platinum tier, maybe they're only looking at a small amount of data, but that can knock over the data warehouse that you're using unless you scale it up very large. And if you scale it up very large, then you have the same over provisioning problems. So cloud, business intelligence is a key workload for this. There's also a model of building SaaS applications where you build an application, and that application wants to show data to end users. And sometimes it's, everybody is kind of looking at the same, they're slicing and dicing the same data. That's also kind of a big compute, small data. And then finally, AI agents. And I'll talk about those a little bit in a second. But there's something in MotherDuck that we do to help make this work. So I mentioned that kind of every user can get their own DuckDB instance, but that can be a pain to provision all of those. And so what we do is, if you enable read scaling, every end user of your BI tool, for example, or your SaaS application, gets their own DuckDB instance, which we can scale up and scale down. We also have mechanisms to avoid overspending, but this allows you to basically scale by running lots of different instances. There's an interesting paper I read recently about, what does it take to build agents? So everybody wants to do agents these days. It's the cool topic. But in order for those to be interesting in analytics, to be able to answer kind of deeper types of questions, like let's say you wanted to say, like, which of my customers is most likely to churn? it doesn't matter how good you are at writing SQL. Like it's pretty unlikely you're going to be able to come up with a single awesome SQL statement that can answer that question. So what you're going to want to do is you're going to want to fire off a bunch of SQL statements, get some answers, make some decisions, maybe pull in data from other locations. And the sort of tenancy model is great for that because each of these agents basically can get a clone of the data. They can even modify the data as they want, and then they can get destroyed when they're not being used. All right, on to the third quadrant. The third quadrant is big data, small compute, and this is very these are very common, and they're basically two really big patterns. The first pattern is independent data SaaS, where you're building a SaaS application where each user has their own data. The second one is time series. Time series, you're creating data over time, but usually you only look at the last hour, day, week of that data. So the first one, hypertendency, can help, kind of this tendency model again, and the second one, DuckLake can work. And I'm going to skip past some of these so we can make sure to get to the demo. I do want to talk about DuckLake. So DuckLake is an Iceberg alternative, and it solves a lot of the problems that are inherent in Iceberg, particularly around transactions, around being able to write data rapidly, being able to do low latency, and simplicity. Like it can be really difficult to set up Iceberg. It can take you seconds to provision DuckLake. So the last quadrant is the big data, big compute. You see this in model training. You see this if you're rebuilding data. Like we talk to people who are like, yeah, these sort of smaller instances are fine, but I have this thing once a week or once a month that I do where I rebuild my data to make sure that that it doesn't drift from the data that I have under the covers. And then you need some larger instances. So one of the things that we do in MotherDuck is we actually have two very large instances. One of them has 64 cores and a quarter terabyte of RAM, and the other one's 192 cores and 1.5 terabytes of RAM. And if you were just going to ballpark compare that to Snowflake instances, that's sort of between a 2XL and a 3XL in terms of the amount of hardware. And there's very few workloads that won't fit in a Snowflake 3XL. So I go back to my old, roots in BigQuery and Dremel. And so Dremel, when the Dremel paper came out, people were amazed by how fast it was. And they showed some examples of a 3,000 node Dremel cluster running an aggregation query over 85 billion records in 20 seconds. So can we do this on a single node? So if you just do the math, that larger instance size that I showed, it has enough CPU, it has enough memory, it doesn't have enough network, but it actually has some pretty big local disks. And so if your data is in the local disks, then we can actually do this pretty fast. So let me switch over to my demo. Hopefully this shows. Cool. So this is the MotherDuck UI, and running SQL queries is usually not all that exciting. So I will sort of narrate what's going on here. So we have a 60 billion strings that have multi-word strings, and we're doing a word count on each one of these. If everything's working, it takes about 20 seconds to compute the word length. This is actually a real benchmark that people use, or that's used in doing term frequencies. So this is a little bit smaller than the table that in the paper. The reason it's smaller is because I ran out of time when I was loading data this morning. But it should scale to the same size. I will show one other thing, which is this is the CLI, because I mentioned latency is important, and so this is a TPC benchmark, we can see the tables here. It actually only took 6 milliseconds to return the catalog of the tables because we actually cache a bunch of it locally. And so, running, I knew that this was going to be benchmark, demo gremlins. Typically, this has been about 38 milliseconds. I'll blame it on the conference Wi-Fi, but you can get very low latency, and this is client measured time. So it's one of the tricks that often database vendors play is they measure time for when they get the query, but we measure time from when the query actually gets sent. This is what this would look like in DuckLake. So in DuckLake, it's a little bit slower. It's about 3 minutes. But to create the DuckLake, just one line of SQL, create that table, and then to take a bunch of Parquet files that we had generated and adopt those is only one more line of code. So we basically more or less replicated the Dremel results. We were a little slower on DuckLake. We were 5x slower on DuckLake, probably 30% slower currently on the DuckDB side. And if we'd wanted to run this in Spark, the same DuckLake in Spark, it would be about 30 lines of code. This is all boilerplate setup. This is the setup for partitioning, and this is the only thing you need to run that Spark over DuckLake. So, small data, small compute. DuckDB is awesome. Small data, big compute. You can use read scaling. Small compute, big data. Hypertendency and DuckLake can really help. And then finally, if you really do have big data and big compute, you can either use these giant instances, or you can use DuckLake with external access and run whatever engine you want over it, Spark, Trino, etc. Thank you, and stop by booth B37 for more info on MotherDuck. Thank you.